So the question 4 seems pretty daunting, but what we're going to do is we're going to take the lessons learned from the previous questions and apply it here. So this is a question about a locomotive pulling 20 cars in a train. So there's 20, and it's asking us for the force that it needs to be pulling at various places. So for part A, they want between the locomotive and the first car, so right there. And then in the second one, it's between the 10th and the 11th. So 1, 2, 3, 4, 5, 6, 7, 8. Now, I only drew 9 cars and I got tired. So obviously, we don't want to have to draw 20 cars and figure all that out. So we're going to answer this question by grouping the variables together. Or sorry, grouping the objects. So in the first part, we're just going to group all the cars together. So here we have 20 times, and each one has a mass of 10,000. So 10,000 kilograms. And if we think about what's the force acting on this, well, only the locomotive force, right? So the force of the locomotive, we're not really, they didn't tell us anything about friction. I'm happy to ignore it. I'm sure there is friction, but maybe that's taken into account with the locomotive force. It doesn't really matter. We're not dealing with it. So it's the force of the locomotive. And then we know that it's going to accelerate, but we don't know what that acceleration is. So first thing we can do is figure out the acceleration. Delta x, delta t, v naught, v, and a. So it tells us it goes from rest to a velocity of 2 in 5 seconds. And we don't care about the distance it has to travel, but we're very interested in the acceleration. So we're going to use the equation without x, but written another way is just a equals v minus v naught over delta t, which equals 2 divided by 5, so we get 0.4 meters per second squared. So that's my acceleration. So 0.4 meters per second squared. Now I have my free body diagram. I'm going to write my Fnet statement. Fnet equals the sum of the forces, which equals ma. So the sum of the forces in this case is, we've got this loco force, F of the locomotive. I'm going to call this direction positive. I just happen to draw the train traveling that way. I'm just going to draw the direction the train travels as the positive direction. So we've got that, and that's equal to mass, which is 20 times 10,000 times 0.4 meters per second. And when you do the math there, you'll get 80,000 newtons. So the locomotive force at that point, force of the locomotive is 80,000 newtons, which is a lot of force. Okay, so then really you can just see that it's quite straightforward now when we have the same acceleration we're dealing with. So if we just look at between the 10th, so if we're going to find out the force between the 10th and the 11th car, what that means is we're going to group, but there's only going to be 10 cars in here, right? So it's 10 times 10,000 kilograms. And then the force is a coupling force, the force of coupling. And it's going to only be pulling that. But now we know the acceleration. It's 0.4 meters per second squared. So when we do the math on this, Fnet equals the sum of the forces, which equals ma. So now the coupling force is going to equal just 10 times 10,000 times 0.4, which equals 40,000 newtons. So the force of coupling is 40,000 newtons in the second case. And I mean, you can see how that could apply to any, it just happens to have been half, but I could have said between the 5th and the 6th car, or any car, it would have been effectively just as easy.